So, hello everyone. Let me first thank the organizers for organizing this very nice school. So, let me present myself. I'm Nicolas. I'm a postdoc at the Observatory of Nice, working with Giorgio, and I will present some very new results that we just submitted in arXiv last week on trying to find the equivalence between 2D, trying to see if 2D classical and quantum turbulence are equivalent from the point of view of velocity circulation statistics. So let me first recall to you the phenomenology of two-dimensional turbulence. So the Navier-Stokes equation, the 2D Navier-Stokes equation can be written in terms of the vorticity field in this form. And in 2D, as vorticity is perpendicular to the velocity field, the vortex stretching term vanishes. And as a consequence, we obtain the conservation of two quantities: the energy, that is dissipated, where epsilon is the energy dissipation rate, and the entropy with beta, the entropy dissipation rate. So to this, it is possible to associate two cascades to these two conserved quantities. One inverse energy cascade that goes as k to the minus 5/3, and direct entropy cascade that goes to k to the minus 3. So this is a schematic picture of a two-dimensional turbulence. If you inject energy at an intermediate scale, you will have energy transfer towards large scales with the energy flux taking negative values, and the entropy will be transferred towards small scales with the entropy flux taking positive values. So we have observed in experiments the formation of two-dimensional quantum fluids and two-dimensional quantum turbulence in different setups. For instance, there has people in Australia and New Zealand, I think they have observed the formation of these large vortex clusters in two-dimensional bosons and condensates. And also, there has been some evidence of the emergence of an inverse cascade in confined superfluids, in confined superfluid helium, and also in the exciton polariton. In terms of numerical simulations, we have studied also the transition between 3D and two-dimensional turbulence in the Gross-Pitevsky equation, where here you can see the evolution of very short vortex filaments, and also in the point vortex model that takes advantage of the idea that in quantum fluids vortices are discrete points. They have observed the formation of an inverse energy cascade and also the development of an entropy cascade. So what's also interesting about two-dimensional turbulence is the lack of intermittency in this system. So what is intermittency? I remind you that in 3D homogeneous and isotropic turbulence, velocity fluctuations are very strong. They strongly deviate from a Gaussian distribution, and they produce the breakdown of self-similarity. Meaning that, what do I mean with self-similarity? Well, if we go back to Kolmogorov 1941 theory, we can try to quantify how are these velocity fluctuations by computing the moments of the velocity increments at a certain scale r. These are known as structure functions, and using just dimensional analysis, one can obtain this prediction that leads to a scaling exponent zeta p that is equal to p over 3 in this self-similar theory. Well, experiments in two-dimensional turbulence and also numerical simulations in the late 90s and early 2000s have shown that in two-dimensional turbulence, there is no deviation from this self-similar prediction, meaning that there is no intermittency, while three-dimensional turbulence, there are some very strong deviations showing that are known as anomalous deviations. So the idea now is to study what happens in two-dimensional quantum turbulence, both in the inverse and direct cascade, and to see if the system is intermittent or not. To do that, we will study circulation, and I will just recall you also the results that Juan presented yesterday. So we know that the velocity circulation defined as a velocity field around a closed loop in a quantum fluid takes discrete values. And we can also compute the moments of a circulation that, using again the same Kolmogorov 41 idea, presents this scaling. This, in principle, can present this self-similar prediction, this self-similar scaling, but in general it presents some scaling lambda p. So computing in 3D, we have observed that computing the circulation around loops of different sizes, the intermittency of quantum and classical turbulence are the same. So the idea now is to see whether in two-dimensional turbulence, classical quantum turbulence are equivalent, what happens with the inverse cascade, and what happens with the entropy cascade. So to do that, we perform numerical simulations of Navier-Stokes and Gross-Pitevsky. For Navier-Stokes, we include a large term dissipation and an extra term given by alpha, that is a large scale friction, and we use 6,000 square grid points. And for the Gross-Pitevsky, we use the standard Gross-Pitevsky equation and 8,000 square grid points. And these are two visualizations of the entropy cascade simulation, where you can see this formation of a large scale, of these elongated structures that take place in both systems. So let me show you how is a typical evolution of Gross-Pitevsky in 2D. So we perform two different numerical simulations. In one, we generate an array of vortices that follow a velocity field that with its energy concentrated at large scales. So you can see here very large scale structures, and if we let it evolve, they evolve in some way. On the other hand, to study the inverse cascade, we want to force, or not actually force, to generate an initial condition at small scales. So this is the array of vortices we generated, and when we let it evolve, it evolves in time, and you can see eventually that the vortices form dipoles that eventually can annihilate and kill each other. So here in this visualization, we observe no sound pulse, because this is just I implemented a filter. This is vorticity, so everything is smoothed out. Okay, so again, we performed 4 numerical simulations, 2 for Navier-Stokes, 2 for Gross-Pitevsky, and in each case, 1 to study the inverse cascade, meaning that we force at small scales, and the other one to study the direct entropy cascade, meaning that we force at very large scales. So here I show you the energy spectrum as a function of the wave number normalized by the forcing wave number. And so let's first focus on Navier-Stokes, which are the orange curves. So we see for large scales or small wave numbers, we see the development of an inverse cascade, and for large wave numbers, the scaling of a direct cascade. On the other hand, for Gross-Pitevsky, we also see in this range of scales the formation of the development of k to the minus 5/3, and in the entropy range, we see the development of k to the minus 3. So that I know this is the first observation of the entropy cascade in Gross-Pitevsky model. And what's also interesting is that we observe, in this case, for instance, the development of 2 other scaling laws, which we can understand here if we know that here is the scale of an intervortex distance, and this one is the scale of the vortex core size. This is the range where we have basically individual vortices. So k to the minus 1 is the scaling of individual vortices, and at smaller scales we have the scaling of inside the vortex, which is a decaying to the minus 3. On top of that, we can compute the circulation. So here we compute the circulation variance, so a function of the size of the linear size of the loops. And again, here we have, for large scales, the scaling corresponds to an inverse cascade, r to the power of 8/3. And on the other hand, at small scales, the entropy scaling r to the power 4 given by a smooth field. And in GP the same. The only difference here that we observe is the scaling r to the power 2, which is basically the probability of finding a vortex at very small scales. Okay, so now, besides this, we can go to high order moments and try just to characterize the intermittency of the flow. So this is what we do. So here on the left, I show you the moments of circulation up to order 16, pretty high moments, and we study in an inertial range between the intervortex distance, which is actually also very close to the initial condition scale and the integral scale, and we compute the local slopes derived as the logarithmic derivative of the moments as a function of the size of the loop. And we see here that they approach a plateau, but that deviates from Kolmogorov prediction. Also, we do the same with the classical turbulence, and we can compute this lambda p, these scaling exponents, which are shown here. So what's interesting here is that in blue quantum and in orange classical 2D classical turbulence display the same intermittent behavior, or a very close, very similar intermittent behavior that is within error bars. And what's also interesting is that last month, I think it was, there were some experiments in two-dimensional and quasi-two-dimensional classical fluids, classical turbulence, where they studied the scaling of circulation. And they reported these scaling exponents that are shown in these green diamonds that are consistent with our simulations. So in general, what we see is that classical and quantum turbulence, both in numerical simulations and experiments, are consistent with each other, and that they are intermittent. So this intermittency is also interesting, that we are still studying it, but this is an interesting regime. So finally, just to finish, we can go to the other regime and study the entropy cascade, what happens there. So in this case, we also compute the moments of circulation in this entropy cascade regime. In this case, we use the extended self-similar method just to compare also with experiments where they did the same analysis. And what we observe here is that both experiments and simulations of classical turbulence display a self-similar scaling in this case that is given by these scaling exponents. But on the other hand, in Gross-Pidevsky, we don't observe that. We have some deviations from the self-similar prediction. And the idea here is that, in principle, entropy in quantum turbulence is not a very well-defined quantity. We know that the vorticity in a quantum vortex is a delta function. So the entropy, which is omega squared, is not a very well-defined quantity. However, one can do a phenomenological assumption that the entropy is proportional to the number of vortices. But what this leads to the fact that for low-order moments and low-order statistics, entropy in classical and quantum turbulence seem to be equivalent, but when we go to high-order moments, they deviate. So, yeah, this is the end of the talk. So we characterize the limits of equivalence between 2D classical and quantum turbulence using velocity circulation. And we studied independently the inverse and direct cascade, where we observed that the same behavior in the inverse cascade for classical and quantum, while a different behavior for the direct entropy cascade. So with that, thank you.